You're listening to ReachMD XM 157, the channel for medical professionals. Welcome to Innovations in Medicine, enhancing the medical community's knowledge of science and biotechnology.
It sounds like something from Mission Impossible or Alias. A contact lens that displays a computer screen could give us superhuman vision and help the visually impaired. I'm your host, Paul Raeburn. It's a staple of spy movies and science fiction shows. Bionic vision that lets the Terminator zoom in on a bad guy or run identity checks on the spot and see the results in his field of vision. Researchers are not quite there yet. I don't think we're going to be building a Terminator on this program today, but they have taken an essential step toward getting there. They've devised a flexible, safe contact lens on which they can imprint electronic circuits and lights. Dr. Babak Parvis, an electronic engineer at the University of Washington in Seattle, unveiled the contact lens at the most recent meeting of the IEEE International Conference on Microelectromechanical Systems in January. And he's here with us now to tell us about it. Welcome to the program, Dr. Parviz.
Hi, Paul.
So tell us a little bit about this contact lens. It's a normal-looking contact lens that's safe for us to pop in our eyes?
Well, actually, I wouldn't probably go that far. It's definitely not to the level that can be used by a human user. We've taken very interesting and promising steps towards having a fully functional contact lens for a human, but we're not at that point yet. We've done preliminary tests on animals.
So tell us where you are now. What have you done, and how have you tested it so far?
We had two goals. One was to make a contact lens that has an embedded display so that you could interface with a mobile computing device, or if you'd like to work on augmented reality, you could use the information displayed right in front of the eye. And the second idea we had was a contact lens that had embedded biosensors, so you could continuously monitor various biomarkers on the surface of the eye and wirelessly transmit that information somewhere else for further analysis. In order to do so, we obviously needed to incorporate a variety of very sophisticated functions onto the contact lens. And what we've done so far is to demonstrate that it's possible to put very high-performance electronics on plastic, to put optoelectronic components such as light-emitting diodes, LEDs, on plastic substrates. We've demonstrated that you could put micron-scale metallic interconnects that you need to build circuitry on plastic substrates, form a contact lens out of those, and we've put that into a rabbit eye, and we've not turned it on a rabbit eye yet. But we've been able to put it on the rabbit, and the rabbit has been happy. We've done tests up to 20 minutes.
Now, here's the problem that we have with people in your field. Electrical engineers and computer people are so adept at doing so many magical things that I can almost sit here and say, well, sure, a contact lens with all kinds of electronics on it. So that doesn't sound like such a big deal. So tell us what were sort of the problems here and the tricks. What made this hard and what makes this an important achievement?
So if you look at more conventional contact lenses, they are primarily made of a polymer, so it could be a hydrogel that the healthcare professionals are very familiar with materials that go into building a contact lens, but it's, for the most part, a piece of material. If we look at electronics, displays, wireless telecommunication systems, they're very sophisticated functional devices. So they're very, very much more complex than just more simple piece of polymer. So if we're going to incorporate those sophisticated functions onto this polymer, we have to have a manufacturing process that can do that. And unfortunately, all the processes that we have, all the methods that we have today to make optoelectronic devices, wireless devices, are very incompatible with plastics. So that was a key technology to develop, to be able to put those things on a plastic substrate and then make a contact lens out of it.
So, I mean, I guess a fair thing to say is that a contact lens by itself, a modern contact lens, is already a very highly engineered piece of equipment that with certain properties in terms of flexibility and permeability and absorption and all kinds of things. So what you're talking about is taking that thing that's been very finely tuned to do a particular job and adding to it wires and metal and lights and other kinds of things that even to us non-engineers sound like they don't fit very well with a contact lens.
Yeah, it was actually, in a sense, it's actually taking contact lenses to the next level of sophistication. You're exactly right. The modern contact lenses have been highly engineered to have certain optical properties and being very biocompatible, so they're comfortable to wear and that has been a major achievement. So we're hoping to add basically onto this achievement by bringing in the whole semiconductor industry onto the contact lens.
For those of you who've just joined us, you're listening to ReachMD XM157, the channel for medical professionals. I'm your host, Paul Raeburn. This is Innovations in Medicine. We're talking to Dr. Babak Parvis of the University of Washington about sophisticated new contact lenses that include electronic devices and might allow you to see something like a computer screen right in your field of vision. What would be the real applications of these in the near term when you're ready to move to humans and put these into practice, which I assume would be a few years down the road? What are the kinds of things you anticipate doing first?
I think having a full-fledged high-resolution display is, as you said, some time away. However, our immediate goal is to be able to turn on just a few pixels on the contact lens and show that this is safe and the user can wear it and it would be comfortable. It would not cause any issues for the person. What kind of information we can show with a few pixels, I guess that depends on the type of gaming or augmented reality or mobile computing device that would interface with it. The second pretty important area that we're pursuing right now is to put biosensors into the contact lens. So we'd like to sample what happens on the surface of cornea. And it appears that a lot of things that happen inside the body also, they are reflected on the surface of cornea. So we'd like to do analysis on the surface, detect molecules, and relay that information out. So that would be an application for continuous healthcare monitoring.
Now, would that be a research tool, or would that be something with therapeutic uses?
I would say both, actually. At least it would allow us to do the type of monitoring that we've not been able to do to this date, because obviously there are various ways to monitor what happens inside the body, and your audience is quite familiar with those. But a lot of times you have to collect a blood sample and do a blood run to see what markers are present. So we can't really do that continuously. If we could do some of those things on the surface of the eye with a contact lens that's worn by a person, and it's very non-invasive, that would be very interesting, because that would allow us to collect an entirely new type of data over a large span of time.
Can you give us some examples of what kind of data you might want to collect and what kinds of pathology that might be important in?
Right now, actually, we're after small molecules. There's at least one small molecule that we would like to measure on the surface of the eye. I would rather not to go into the specifics because we haven't done it. But we're hoping that this would be a fairly quick thing to do, and hopefully we can present our results in a fairly short time period.
Could this be the kind of thing that could monitor changes, say, leading up to macular degeneration, or pressure or dryness, moisture, those kinds of things?
Yeah, actually, it's absolutely possible. There are a variety of transducers that we could incorporate on the contact lens. Pressure sensing is definitely something that we've looked at, and we're interested in doing that.
So not here yet, but a possibility.
Yes.
If I'm looking at something 10 feet away or out at infinity or even closer, I'm not focused on the surface of my eye. So how does that image get to me and be clear?
If we just put pixels on the surface of this contact lens, it's not going to be possible for us to focus on the image. So the image will be blurred, and at best we may see some color changes, but not form a very useful image. So we have two approaches for correcting this problem. One is that we have the ability to make very tiny lenses for each pixel on the contact lens. So you can have an array of potentially thousands of lenses that are just a few microns across. We can put that on each pixel, and they would manipulate light in a way that would create the perception of having an image that's a bit further away from the eye.
And you could put that image as close or as far away as you wanted to, depending on which lens you used in there.
That's right. We're designing actually those adaptive lenses right now that you could incorporate in every pixel, so we can manipulate the light that comes out of the pixel. So that's one way to do it. And the second way to do it is the same way that we made the diodes, the light-emitting diodes. We can make very tiny lasers, and those don't need lenses anymore. So they would directly direct the light from each pixel onto the retina. Obviously, very low-power laser and safe ones, but that's also possible because we could make arrays of lasers.
Two very basic kind of questions occur to me, however, that I don't think we've talked about. One is, how do you provide power for this thing, and how do you communicate with it?
So we have two ways that we're looking at right now for powering up the lens. It's a standalone device, so it has to collect its power from outside. Initially, we did look at batteries, and it's a bit problematic to put a battery on a contact lens because of the chemicals. Ensuring that the battery is nicely encapsulated and it doesn't leak out on the lens is a bit difficult. So we've We've looked at building small antennas on the contact lens and harvesting radio frequency energy from the environment. And we have actually working antennas right now, small antennas on the contact lens that can collect RF radio frequency energy and turn that to useful power. So that's one way to do it. The second way is to collect light and convert that to useful power. So that's something similar to a solar cell. And we have also micron-scale solar cells that are working in our lab. So they can collect light and turn that to a power that a system or a contact lens can use.
So that might be the kind of thing particularly good for some application in daylight or driving during the daytime or something where the thing would light up when it was in daylight but not necessarily inside or in the darkness or something.
Yeah, obviously if you're in a dark room it won't be useful, but our hope is that the regular level of light that you have in a normally lit room would be enough actually for us to power our systems. In terms of telecommunications, there are collaborators in this project. I have to also mention that this is not work, obviously, by one person. There's a fairly sizable group working on this. And we have excellent faculty members in our university who are interested in very low-power telecommunication circuit design. So that's the type of problem that they're looking at to design the telecommunication link for the contact lens. But that's a bit out of my area of expertise.
But it's possible, or the things they're doing lead you to believe that some of that work will be ready when you need it.
Absolutely, absolutely.
That's all the time we have. Thanks so much for being with us. We've been talking to Dr. Babak Parvis of the University of Washington about computer screens and computer images that might be implanted right on a contact lens. Thanks for being with us.
Thank you, Paul.
I'm your host, Paul Raeburn. For comments and questions, check us out online at reachmd.com, where you can see a program guide, past shows, this show, download podcasts, all those nice things. Thanks so much for listening, and we hope to see you again real soon.
Thank you for listening to Innovations in Medicine on ReachMD XM 157, the channel for medical professionals.
You're listening to ReachMD XM 157, the channel for medical professionals. Here is a sample of the great shows airing this week.
I am Dr. John Armstrong. Join me this week for Heroes in Air Force Medicine with my guest, Lieutenant Colonel Cynthia Cogburn, as we discuss the role of Air Force veterinarians in the public health.
This is Dr. Leslie Lunt. Join me this week on the Clinicians Roundtable, where my guest will be Dr. Stephen Schroeder. We will be discussing how we might attack the obesity epidemic.
And this is Dr. Bruce Bloom. Join me and my guest, Dr. Elizabeth McNally, Professor of Medicine and Director of the Institute for Cardiovascular Research at the University of Chicago Medical Center in Chicago, Illinois, where we talk about inherited heart diseases.
Throughout February, ReachMD XM 157, the channel for medical professionals, presents a special series exploring heart health. For our complete weekly guest and program guide, and to send us your comments, visit us at reachmd.com.